about the assignments, or yeah, the announcement slide. So basically, today we'll definitely finish the chapter on telescopes, light and telescopes, and then when we should begin the next chapter. The next chapter is on the formation of the solar system, which is kind of fun. So we end up this unit with chapter 6. The other thing is, remember the at-large labs? There was like a moon journal that you guys could do for 2 weeks, okay? And I said you need to begin it about first quarter. Well, it's about first quarter, okay? So basically, you're going to need to find the moon and tell me kind of how high it is. Maybe, I think I'm going to have you sketch how full it is, okay? Tell me, can you use a camera?
I have a $2,000 camera, so yeah.
Yeah, you can use, he's asking instead of sketch, can you take an image? Definitely, that would be awesome. And kind of the direction of the sky it is, okay? So it's all kind of in the, if you have any questions about the directions, let me know. But if you, that appendix that I gave out the first day should have it. Is an at-large lab. Then Wednesday, we're going to finish up Unit 2. And then after class, if you're interested, we're going to do a review session in the Chem Lab, which is 512. And I will tape that so you can have it later, you know. At a review session, what we'll do is go over that sheet that I gave you for the kind of key terms on your unit exam. So this is what we'll go over for a review session. We did the review session last time, so I think it's kind of helpful.
And that's immediately after class?
Right, that is. Looks like I have a mistake here. This actually, I just changed it here. The Moon Lab actually should be Thursday, not Wednesday. My bad. So you're like, man, I thought I figured that one out. So Thursday. Thursday evening, 9:30, will be Moon Lab here. Now, since this is our second go at it, it's a go regardless. If it's looking like it's going to be cloudy and we can't use the telescopes to see the moon, I'll reserve a room and I'll kind of give you information on where to come for the room. Okay? You know what I'm saying? Yeah. The forecast right now is partly cloudy, so I'm hopeful. But, okay? And then Friday, your chapter assignment for chapter 6 is due, and then come in and take your next unit exam over chapters 4, 5, and 6. That work? Okay. So this actually is a review slide, just to kind of get us all on the same page here. We ended with this slide last Wednesday when we met. Okay. A telescope that's gathering light anyway, and actually we're going to talk about telescopes that gather other forms of energies. But a telescope that gathers light can either be a reflecting telescope using mirrors or a refracting telescope using lenses. Okay. But what they have in common is that you use a telescope to gather photons, to gather information from little distant objects. So that allows you to see things more brightly, and you can see more detail, and you can see things that at a greater distance. So starting with a refracting telescope. So a refracting telescope uses a lens. Okay. Oh, sorry, that's coming up. Did we do this one too? No? Okay. Whether it's a refracting telescope or a reflecting telescope, this one isn't geared one way or the other. Okay. But the whole seeing detail that I mentioned on the previous slide, the second, brightly seeing detail, seeing things at a greater distance, that the ability of a telescope to see detail is called its angular resolution. So basically, if it looks kind of blobby and you can't tell the difference, for instance, if you're looking at Jupiter, you can't tell the difference between its bands, okay? That's poor angular resolution. If you're looking through a telescope at Jupiter and you can distinctly see some bands, or if you're looking through a telescope at the sun and you actually see sunspots, okay, that is good angular resolution. The more detail you can see, the smaller the angle between objects, that means it's really good. So small angular resolution is good. So in general, the bigger the diameter of the mirror or the lens, then the better the angular resolution. Sometimes students say, well, now I want to buy a telescope, what should I get? And I think maybe haven't told you guys yet, but I usually steer them towards binoculars first. There's a lot of neat things that you can see with binoculars. Binoculars help you find your way to star hop to where things are in the nighttime sky. But aside from that, the bigger the better, it's true. But the problem is if you get a poor quality, large diameter mirror, you know, you're no better than getting a great quality with a smaller diameter. Okay. So, refracting telescopes, those that use lenses. For these sort of telescopes, basically you're going to find the light kind of what we say converge, okay, on the backside of the lens, okay. The reason that light comes to what we call a focal point, okay, so here we just have a slab of glass. This is not for a telescope. But over here we have a glass that's actually been ground. It's like a double convex, okay, sort of situation. Now, when light travels from air to glass and from glass to air again, kind of like you see in this first one right here, it's bent. Can you see the light being bent? It's going here, and it's going this way, and it's going this way. Okay, light is bent in that slab. The shape of this lens is such that light is, again, bent twice, but it's bent back to a focal point, and that's the important part of a telescope. Okay, so all of the light coming in the shaft, all those photons of energy are basically squished down to that one place, the focal point. It's concentrated. Okay, so when you're looking at a telescope, refracting telescopes are notorious for having long optical tubes. The optical tube, just at the end of the optical tube is the lens, and at the butt of the optical tube is where kind of the focal point can be unpacked with an eyepiece. Okay. So that's a refracting telescope. I get my refracting and reflecting mixed up sometimes. So I mentioned a long optical tube. Okay, the optical tube is just simply giving the light time to go ahead and converge to a focal point. So this one kind of drawn to scale. Can you see this little person down here? Okay, little tiny person. This one is kind of in the Chicago area. Road trip. And of course the lens is up at the top here. And I've probably already mentioned this, but kind of the housing for a telescope like this is called a dome. Okay, so you can kind of see the dome going around like that. Domes are great because they house the telescope, but they need to have some sort of slit, okay, in them. So basically when they're in use, the slit is open. And then what happens is that dome can rotate. You put the slit where you want the telescope to look. If you do any, like going to an observatory like this, please know that they're not air conditioned and they're not heated, because that plays havoc with the image you're trying to see. So they kind of have to be conditioned for the air outside. So that is that. One other thing, notice that this says it's the largest refractor in the world. Like, really? You couldn't get larger, and I don't have my yardstick, but you couldn't get larger than a meter for a lens? Well, you could, but the problem is that glass is actually kind of a slow-moving, glass deforms over time from gravity. So there is a limitation. Now, what we're going to see is that telescopes that use mirrors, not so much of a problem, okay? And we'll kind of take a look at that now. So mirrors don't have the same problem with their deformation as refracting telescopes do with lenses. So this is what a kind of the inside of a reflecting telescope would look like. So now this uses a mirror, okay? So basically, and I brought one the other day to show you a reflecting telescope. But basically, the light comes down the optical tube. It goes to the back of the optical tube, okay? And then actually that image is focused forward. So here the focal point is kind of in front of the light gathering object, okay? So the focal point goes up there, and then we just need to unpack it from here. Unpack all of that light that was gathered to the focal point, one way or another. So this actually, preferably the shape of the mirror is what we call parabolic, okay? But it's easier to grind, and by the way, a mirror, this is just a regular old mirror. If you were going to make a mirror, what would you take? You'd take a piece of glass and you would put silver on it, okay? And that's actually the way mirrors for telescopes are made. So they take a piece of glass, they make it the right shape, and then they silver it. But it's a lot easier to make a spherical shape instead of a parabolic shape. So a lot of times they're just kind of spherical, and then they actually correct for the spherical nature with a correcting plate. And that's actually, the schools does that. It's got a Schmidt correcting plate on it to kind of correct for it not being parabolic, being spherical. But anyway, it works this very similar way. So light comes down, it goes back to a focal point. There. Now, the thing is that there are four, and you don't have this slide, there are 4 ways to unpack that image from the focal point. Again, you don't have this slide, but just bear with me. Here's the 4 ways, starting from left to right. This is the most common way to unpack that information of focal point. The one I brought in the other day, actually, is this one, though. So you see A and C up here. A is a Newtonian design. C is a Cassegrain design. It's just, what do you do with that, the image or the information at the focal point?